For decades, the standard model assumed the universe was a static, silent void, a perfectly still body of water, undisturbed by movement or sound. That perception was wrong. The universe is actually churning with activity. Massive cosmic entities collide, sending heavy, chaotic ripples of gravity expanding across space. This silence was a limitation of our own biology. Human technology simply lacked the sensitivity to hear the low-frequency cosmic hum produced by the most massive objects in existence. The source of this hum is the merger of supermassive black holes, giants billions of times the mass of our Sun. Found at the centers of colliding galaxies, these pairs spiral toward one another for millions of years. As they orbit, they churn the fabric of the universe itself, sending out ripples of gravity that stretch across millions of light years. Current technology, like LIGO, the Laser Interferometer Gravitational Wave Observatory, is built to catch the quick, sharp chirps of smaller black hole collisions. But ripples from supermassive black holes are too large for any terrestrial machine to measure. A single wave can take years just to pass by, making it invisible to a detector that is only a few miles long. Detecting a wave the size of a galaxy required a different approach, turning the Milky Way itself into a scientific instrument. Constructing a detector on this scale is possible because of pulsars, the dead, highly magnetized remnants of massive stars. These objects spin incredibly fast, sweeping rigid beams of radio waves through space. Every time those beams sweep past Earth, we record a pulse. The arrival times of these flashes are as predictable and precise as our best atomic clocks. This network of perfectly timed, spinning stars provides the rigid framework necessary to measure the warping of space across the galaxy. The NANOGrav project, the North American Nanohertz Observatory for Gravitational Waves, monitored this array of pulsars for 15 years, watching for their perfect timing to fail. As low-frequency gravitational waves roll through the galaxy, they physically warp spacetime between us and the stars. When a ripple expands space, the distance a pulsar signal travels increases, arriving late. Conversely, a wave compressing spacetime decreases the distance, causing flashes to arrive early. Finding this specific, synchronized pattern of early and late flashes across the sky proved the existence of the cosmic hum. By tracking these anomalies over a decade and a half, scientists successfully utilized the Milky Way as the most massive scientific instrument ever operated. Confirming this background hum proves that the universe is not a silent, empty void. This discovery provides access to an entirely new spectrum of gravitational astronomy that was previously out of reach. Observing these low-frequency waves allows us to record the history of how the largest structures in existence, galaxies, merge and grow over billions of years. Our view of the cosmos has moved past the idea of a still pond. We now see a universe defined by constant, rhythmic activity. We have successfully tuned in to the rhythmic soundtrack of the cosmos, providing a new way to understand the evolution of the night sky.